You know, this Jasmine Butler character's never showed up. I hate that because I put their name on the list, and throughout the whole semester I have to put absent. You know, it makes for a lot of work. George Smith. But you're not even in the class.
I'm not.
All right, so we're going to talk about fluid molecular. You know, fluid. In a sense, our body is just one big old bag of fluid. That in an average adult male, 60% of our body weight is just water. Isn't that incredible? 60% of our body weight, we're just water. We're just big old sacks of water. Now, for females, why is it that only 50% of their body weight is composed of water?
Because they have more fat.
Yeah. Yeah, they have proportionately more fat, whereas an infant has very little body fat. So 70% of their weight is water. In fact, that's why infants, because they don't have much subcutaneous fat to insulate them, to protect them from heat loss, that's when we bring them outside, we swaddle them. Okay, because they don't have much protection, much fat at all. Of course, these percentages can change depending upon whether the patient's thin or obese. Okay, but all that water is contained within 3 large fluid compartments. Now there's some other smaller fluid compartments, but these are the major 3. If 60% of our body weight is water, then 2/3 of it, 40%, is found within the intracellular fluid compartment. In other words, that water is found within cells. So the largest of these 3 fluid compartments is the intracellular fluid compartment. The other third is found within the extracellular fluid compartment, okay, which can be subdivided into interstitial fluid and intravascular fluid, or plasma. With respect to that extracellular fluid compartment, 80% of that fluid is found in the interstitial fluid, tissue fluid, between cells. The other 20% is found within the bloodstream. We call it plasma. Okay. Now, in general, fluid moves between these compartments following osmotic pressure. Depends upon relative concentration of solutes within the various compartments. Okay. So it says water moves freely from one compartment to the next. Okay. Why? Since all membranes have channels for water that allow water to follow its osmotic gradient. So it says the principal force that determines the movement of water from one fluid compartment to the next is going to be osmotic force. Okay. Water tends to move from the compartment where the number of particles per milliliter is the greatest. This goes back to that little beaker we showed earlier in the year. Maybe it was last semester. We have a beaker, and if you separate it into 2 halves by a little semi-permeable membrane, and you dump solute particles on one side, but not on the other. And this membrane is permeable to water, but it's not permeable to the solute, then water's going to tend to move to the compartment where the solute concentration is the greatest. That's osmotic force. And so the same thing happens between fluid compartments. So for instance, normally the osmolarity, or the solute concentration within the different compartments, is relatively steady. They're in equilibrium. Meaning that the concentration of solutes inside and outside the cells is about the same. But if someone were to suddenly be administered a hyperosmolar solution, meaning a solution with a high solute concentration, such that this fluid was administered within the bloodstream, suddenly the bloodstream, the plasma, would become hyperosmolar, have a higher concentration of particles than the surrounding compartments. So what would happen? Water from the interstitial space, the interstitial fluid compartment, would begin to move into the bloodstream. Okay? Now, when that happened, what would happen to the solute concentration within the interstitial space? It would increase. Why? Because you're maintaining the same quantity of solute, but it's being dissolved in less fluid now because that fluid is being moved. And so the solute concentration increases, and so then what happens? We have movement of water then from the cells into the interstitial space. So that administration of the hyperosmolar solution is going to have an impact upon both the interstitial fluid and the intracellular fluid compartment. Water is going to shift based upon solute concentration. So all of these particles, all of these solutes create osmotic force. In fact, the osmotic force is the sum total of all of the solute concentrations. Now, what are these solutes? In the extracellular fluid compartment, that means the plasma and the interstitial fluid, the principal osmotic particles are sodium, chloride, and bicarb. Okay. In fact, of these, the sodium is the most heavily concentrated. Whereas the situation is different in cells. In cells, the solute with the greatest concentration is potassium. Whereas inside of cells, we find very little sodium. Okay. You can also find magnesium and phosphate and proteins inside of cells. Whereas outside of cells, potassium concentration is very small. Why is it that potassium is so heavily concentrated inside of cells and sodium outside in the extracellular fluid compartment? What's the mechanism? What's the reason? Yeah, sodium-potassium pumps. All cells have sodium-potassium pumps that tend to bring potassium into the cells and in turn pump sodium out. So sodium is going to be heavily concentrated outside of cells, whereas potassium is just the opposite. It's inside the cells. In fact, this is kind of a bar diagram that depicts the situation. It depicts the fact that way over here on the right, inside of cells, look, potassium makes up the greatest concentration of cations. What are cations? Positively charged ions. Next is magnesium, but look here, very little sodium. Okay? Now generally within compartments there's an electrical equilibrium, so that every positively charged ion has a negatively charged. Okay? You have a lot of phosphates and sulfates, but look here, protein has a relatively high concentration of cells, but if we go into the interstitial space, there's very little protein. In fact, we don't see any mentioned here. And the reason here is that protein is generally synthesized inside the cell, and it's too big a molecule to leave. So we don't find a lot of protein in the interstitial space. Now, again, the interstitial space and blood, they're part of the extracellular fluid compartment. This is where the sodium concentration is much higher. And the sodium, these positive ions, are going to be matched by negative ions, principally bicarb and chloride. You're going to have a little bit of protein in the bloodstream because some cells produce protein. And the liver sometimes produces proteins that's released into the bloodstream. Okay? But you're not going to find much protein in the interstitial space. Okay? Now, when you look at a lab report, and a report, if you're performing serum chemistries where you're measuring concentration of different chemistries, like sodium, potassium, chloride, bicarb, calcium. Okay. Generally, these electrolyte concentrations are expressed as milliequivalents per liter, which reflects the number of electrical charges in a liter of solution. Okay. For example, example, if you take an ion like calcium, okay? Calcium has a 2+ valence, 2+ charge. And so if you simply were to count the number of particles dissolved within the solution, you would have X number of calcium particles. But if you were to quantitate in terms of milliequivalents, because there are 2 charges per each particle, it would have twice the number of milliequivalents. So if we quantitate calcium in terms of milliequivalents, it's twice that if we were simply to calculate in terms of moles, let's say. Okay. And we use milliequivalents because the physiologic effects of various electrolytes are more a property of their charge than are their number or weight. Whereas if a molecule doesn't have a charge, oftentimes the units are expressed more in terms of the weight, like grams per deciliter or milligrams per deciliter. Here we're looking at a cell sitting within some interstitial fluid. Notice that the major intracellular solute is potassium. Outside the cell, the major interstitial solute is sodium. But notice here that the concentration of sodium and potassium are relatively the same. And so there's no net movement of fluid. The same amount of fluid that's leaving the cell is in equilibrium with the fluid that's entering the cell. So we have a state of equilibrium here. On the other hand, in this next picture here, we see a cell that's sitting within a hyperosmotic environment, or a hyperosmolar environment, where the concentration of particles outside is much greater than that within. Okay? So that creates an osmotic gradient that draws water out of the cell, and so the cell shrinks until an equilibrium is achieved, until the concentration of solute inside and outside is the same. The opposite would happen if you place the cell into a hypoosmolar environment, where the concentration of solutes is less than that within the cell. In that case, water is going to move into the cell, and it's going to make that cell swell. Why? Because human cells, unlike bacterial cells, don't have a cell wall. Okay? That creates a back pressure. In fact, some human cells, if you put them in an environment that is hypoosmolar enough, the cells will burst. They'll undergo osmolysis. Okay. Now, if a person comes into the hospital with a fluid or electrolyte problem, oftentimes their initial orders will include the measurement of strychnine-O's. You ever heard of INOs? What does that stand for?
Intake and output.
Yeah, intake and output. So the nurse will be given orders to measure everything the patient takes in and puts out. Now you'll know that because if you look at the door into the patient's room, they'll have a little tally sheet like this. And on one side will be I's, the other side will be O's. And that information about strychnine-O's is passed on to the dietitian so that even when they bring a plate of food, the dietitian will quantitate how much fluid is on that tray. If it's a bowl of soup, she'll say, okay, the soup has 100 milliliters. You know, the 8 ounces has 240 milliliters, let's say, whatever it is. Okay? She'll quantitate, and then the nurse's job is then to go in after the meal and to see what percentage of that fluid intake was actually consumed by the patient. And she'll write down, okay, breakfast, the patient drank, had 600 milliliters. And she'll quantitate for breakfast, lunch, and supper, and anything in between. And at the same time, if the patient puts out anything, that has to be measured. So the nurse will tell the patient to, if they use the toilet, for instance, they'll put a hat seated within the rim of the toilet. So their output doesn't go into the toilet, it actually goes into this little hat that has little calibrations so that the amount of volume can be measured. Okay? So that I and O's are closely measured. Okay? Now, most intake, fluid intake, water intake, comes from your diet, food and beverages. A small amount of your water intake is a result of metabolism. Okay? You know that when you break down one molecule of glucose to produce ATP, you also generate 6 molecules of CO2 and 6 molecules of water. So about 10% of new fluid intake, it's really production here, comes from metabolism. So we call it metabolic water. What about output? Most of your output, not surprisingly, comes from urine, 60%. What is surprising is that the next highest amount, 28%, comes from what are called insensible water losses, meaning that these are losses that you can't actually see. They're often in the form of vapor, water vapor, principally from the skin and lungs. You lose water vapor in a significant amount. Now, if someone has a problem with the skin or lungs, let's say somebody has a third-degree burn over 60% of their body, then they can have a much increased amount of insensible water loss through skin because you don't have that protective barrier. Or if someone's on a ventilator, generally they can have more water loss through the lungs. Sweat accounts for a small amount, feces a small amount, but in a normal individual, our body balances intake and output. Through things like thirst and ADH. If we're taking in less fluid than we're putting out, what happens? We start to develop a negative balance and we become thirsty. Start taking in more. So that over time we balance intake and output. Oftentimes, when you look at these charts, I knows, you'll see that there's more in than out. Right? And part of that is because we're not accounting for insensible losses. So a common practice is to add, let's say, 500 milliliters to your output to account for those losses. This is a nice picture that shows the relative quantities of fluid intake and output.